So we are going to have a look at regression, and I would suggest there's two key reasons you might be doing a regression, and one is to predict something and the other is to explain something. So the context we looked at correlation is we might want to predict an individual's systolic blood pressure given their BMI, or we might even want to predict a reference range for their systolic blood pressure given their BMI. So that's very much in the context of prediction, and this is something you're very familiar with from all the calibration curves you construct doing lab tests. You're trying to produce a formula that takes one measure in and allows you to predict some other quantity. But the other reason for doing regression is purely to explain something. We might only be interested in explaining how much, on average, our systolic blood pressure increases for a unit increase in body mass index. So we don't have to do all of this. We can do one, or we can predict, or we can explain, depending on the application. And it's the same technique that gives us both. And I have plotted I have fitted a regression model. The command in R that lets you do this is LM. That's a lowercase l linear model, and I'm telling it to regress. I think is the nomenclature. Regress Omron recorded systolic blood pressure value on the BMI value. There's a formula in there that's saying regress Y on X, and the data that I'm using is the Health Survey for England data. And when I fit that model, it gives me a blue line with an equation, as it says there, y hat, the fitted value of y, that's the expected or the average value of y given BMI, is 92.12 plus 1.18 multiplied by your BMI. So in other words, for a unit increase in BMI, our systolic blood pressure increases on average by 1.18. And a bit of jargon that's important to have here, this Y with the what looks like a French accent, the Y hat, we call it, is the fitted value. It's the average value of BMI, of systolic blood pressure for a given BMI. And again, you can make your judgments as to how faithful a representation that blue line is of the data. Because when you use that model, what you're saying is, I can throw all my data away now. All the information I need to understand the relationship between these two variables is captured by that formula. Y hat is 92.12 plus 1.18 multiplied by BMI. So that's the model, but we can do a few more things with the model. And if it's a statistical model, we can do more than draw a line. We can draw a confidence interval around that line. So this is telling us something about the uncertainty around the fitted values. So I'm actually saying, this is one sample from a population. I could get another sample. I'd get a slightly different line, but 95% of the time I would expect that line to lie within that narrow grey band. So it looks like we've enough data to estimate that relationship with some precision. So that's the confidence interval in a regression context. It's an interval for the fitted values. It's an interval for the line. It's telling us all about the average. Whereas we can also get a prediction interval, and this tells us about the uncertainty for a randomly selected individual. So if I selected somebody with a given BMI at random, that's telling us the range of systolic blood pressures I would expect to see for that individual. And that's somewhat akin to your reference ranges. So, but in regression model terminology, this is a prediction interval. So we have confidence intervals that tells us all about uncertainty in the blue line, and prediction intervals tells us about uncertainty in individual people, the individual data. So just to make this maybe a little bit more specific, I can create a prediction from R using the commands that are shown there. I create a data frame with a column called BMI val with a single observation 25, and I use a command called predict to predict the value of Y given this new data, and I tell it I want a prediction interval, and when I do that I get a prediction interval that's 89.8 to 153.7. So I'm saying if I had an individual with BMI 25, my 95% prediction interval for that individual's systolic blood pressure is 89.8 to 153.7. So that's not an average individual, that's a real live individual. That's my prediction interval. And recall that the expected or average, the fitted value, this y hat, was 121.7. So the average, I'm saying the average value of systolic blood pressure for an individual with BMI is 25, but there's a prediction interval for the likely values I would expect to see. Now, I talked about this fairly lightly in the lecture, but I thought I should add, in case, just a little bit more precision here. So essentially we've got this model that says the systolic blood pressure can be predicted by alpha, Greek alpha, some kind of unknown intercept, plus beta, Greek beta, some slope multiplied by the body mass index, plus some unknown error that allows for individuals all varying. Now if that model's okay, and I put it in R, I get an output that tells me I get a slope of 1.184, and that slope has a standard error of 0.04, and with those two numbers, that gives me a t-value of 29.928, and we can use that very much the same way we use t-values in t-tests, and that will tell me the p-value is exactly is 0.000 to 3 decimal places. So I don't know what that is exactly, but it's definitely much less than 0.05, so I can reject the null hypothesis, and basically doing a formal test, I'm saying that slope is not zero. Might not know exactly what it is, but it's not zero. There is a relationship between BMI and systolic blood pressure. The other feature that we get out of models that can be interesting is something called an R-squared value, and it's loosely referred to as the percent of variation in systolic blood pressure explained by the BMI model, and in this case we get an R squared of 15.5%. So it sounds like we're not explaining much of the variation in BMI by our model. And again, likewise, there's a confident command in R. We could get a confidence interval if we wanted for the slope. It's 1.107 to 1.262. So, you know, we're saying that on average, you know, you definitely gain a millimeter of mercury for every unit increase in BMI on average. What's much more important that I did explain a bit more about in the lecture is that in order for any of this statistical stuff to work, you have to make assumptions. You can always draw that line and say it's a line of best fit because it's got some really nice geometric properties. But if you want the statistical stuff to work, if you want the confidence intervals to be valid, if you want the prediction intervals to be valid, you have to make assumptions basically about the errors. And they amount to saying, I assume we have zero mean errors. I assume that the errors are constant variance across all values of predictor variables or all values of the fitted values. And I also have to assume that the errors are independent, which means basically that observations are independent. So zero mean errors is really hard coded into the calculations. There's not much we can do to worry about that. However, independence is something you have to assess by thinking about the design. And in this case, this was a random sample from the English population. It's not like, for reasons of cost effectiveness, I went to a gym and measured everybody in there, and then I thought, oh, I'd better balance that out by going to stand outside of McDonald's and do everybody's measurements there, where there might be non-independence because we might find the the all the people in the gym tend to have lower BMI than all the people in McDonald's or whatever. What we do have random samples here, so that's great. The observations are independent. And again, usually in science, you can decide whether the observations are independent or not by the way you design the experiment. So the only thing we need to check routinely is whether the variance was constant, and that's best illustrated by a plot. And this is the simplest of all possible plots. There are refinements to this if you want to go on, spend the rest of your career improving this, but essentially the x-axis is my fitted values. So this is the model, this is the prediction I get from x, but I'm looking at y hat, I'm looking at people's predicted BMI, and then I can look at the residuals. And what I really want is I want constant variance. I want there to be as much spread in the residuals at low values, low fitted values, as there are at high fitted values. And it's not clear what's going on, but I can say that is definitely not a textbook example of a good residual plot that you want to see that says, yes, I have a valid model. The textbook problem is something where the variance increases with the fitted values. It increases with x and hence increases with the fitted values. And you're looking for a very distinct fanning out. So I could draw a line going from the middle upwards, middle left upwards, and the middle left downwards. And well, it doesn't look a lot like that either. And it could just be there aren't many people of very high blood pressure anyway, so that's why we don't have any here. So it's difficult to call that, but that's definitely not textbook perfect, and it's definitely not got some obvious textbook errors that you can fix. So it tells you have to be a little bit cautious with confidence intervals and prediction intervals that you've got from that model. I would say it's not really good enough to derive prediction intervals from. There's some caveats in the assumptions you made, and really, and this goes way beyond anything you have to worry about at undergraduate level, but if you were offering this as a tool to GPs, that now needs more work. So again, what are we looking for you at the moment? We're just looking for you to know that you're making assumptions, you check the assumptions, and there's some ambiguity there. You can just hold your hand up and say, well, it's not clear. It's not clearly awful, but it's not clearly right either. And that's good enough for the moment. So to summarise everything we've done, especially when you're dealing with just correlation, be cautious. Always ask to see the data. And also be cautious about study design. Interestingly, regression itself was really designed around controlled experiments. It wasn't designed for the kind of observational survey data that we're looking at in the Health Survey for England. I mean, it's completely standard to use it there, but it wasn't originally designed for that. So if you can use a good study design, like a randomized controlled experiment, you get all kinds of benefits. In terms of regression, it's good to know the difference between a regression you're using to explain something. I'm going to explain this phenomenon that as people's BMI increases, on average, their systolic blood pressure increases. That's an explanation of a phenomenon. Or you're trying to make a prediction. So you're doing a calibration curve on some lab work. Or I might want to produce a 95% prediction interval that lets me construct a reference range for blood pressure for individuals of different BMI. But the main summary of this week, it matters more than anything, always plot your data. Always, always, always. Don't do any of this stuff at all without looking at plots of your data. And it might sound like I'm overemphasizing the point, but in scientific publications, people just go and report the results. And that's best practice in terms of publication, because it's a huge waste of paper and ink to put all the various plots in that you might have need to have done. But you have to be reassured those plots were done and were checked. Otherwise, it's bad science. So you can get an impression from reading a lot of scientific material that plotting's not that important. But the reality is it's always there. If it's valid science, it was done. It just wasn't necessarily printed up in the journal for reasons of space and ink. Plot your data. Otherwise, I had some brilliant questions during the lecture. Thanks for that, and good luck with the rest of your study.